Hello everyone. In this section, we're going to solve constant coefficient homogeneous differential equation. Firstly, I'm going to let you know the goal for this section. We want to solve linear differential equation of order n. Let's take a look at the general form for differential equation of order n. So it's going to be like this one: y to the nth derivative a n. So here's a1 and a2 plus here it is a n y, okay, and equals, this is non-homogeneous if the rest set doesn't equal 0, right? So today we're just going to solve all the a's. They are all constant. Okay, they are all constant. All the a1 till an are constant. And capital F equals 0. In the next section, we're going to solve non-homogeneous. Okay. Now let's take a look at this homogeneous system. We are going to write down this system into operator way. So we did that in 8.2. That means we are going to put this into like P D y equals 0. So PD means a polynomial. So this means polynomial of D. And what's D? D means the operator, derivative operator, like D squared equals what? The second derivative of a function, right? Something like that. Okay, and so we can write this differential equation can be written as what? Let's see. D to the n plus a1, D to the n minus 1 plus just an at the end. Okay, and y equals 0 if it's homogeneous, right? So you can see this is a polynomial of the PDY. So let's take a look at definition. Now let's take a look at definition 1. So PD equals this one, D to the n plus a1 t to the n minus 1 plus an minus 1d plus an. Okay, this is a polynomial. This polynomial is called a polynomial differential operator. So it's called a polynomial differential operator. Okay, and corresponding to this PD, if we replace all the D by R, so it's like we change all the D into the R. If we look at the polynomial, it says R to the n, a1 R to the n minus 1, right? And a1 R plus an. Okay, this is called auxiliary polynomial. This is called a polynomial. Okay, and if we make the PR equals 0, then we get equation. For example, like if we have, before we solved this kind of thing, r squared minus r minus 2 equals 0. Okay, something like this. This is PR equals 0, right? And the corresponding polynomial equation. So this is the corresponding polynomial equation. Is called auxiliary equation. Okay, so that's the definition. Let's see, it's called the polynomial differential operator, polynomial equation. Okay, And we can, before I give you the example theorem, we can do like we can take a look at one example, kind of like example. Let's take a look at this one. This is differential equation with order 2 and it's homogeneous, right? And we want to write down this into operator way. What is operator way? That means we can write down this as d squared minus d minus 2 and y equals 0, right? So what is PD? PD is d squared minus d minus 2. And the corresponding auxiliary polynomial, we just change d into r, so r squared minus r minus 2. And if we want to have the equation, so we just make that into 0. So, right? So this is the example for the definition 1. Now let's take a look at the theorem 2. Theorem 1. Okay. Let's see. Okay, PR can be factored as this form. Okay, PR, this is general form. R minus R1 to the M1, R minus R2 to the M2 power, R minus RK to the MK power. So if we look at this example, that is like PR, if we factor that out, is R minus 2, R plus 1, right? So it's like a M1, M2 is like a multiplicity. They both are 1, so the power both are 1. But sometimes they may be different power. Okay, in general case, it's just like this way. And all the M1 plus till MK will be power n. So totally the power will be n. So like here's 1, 1, and 1, and 1, which is power 2. Something like that. And now the following differential equation, okay, the differential equation. Differential equation is like this one. D minus R to the my equals 0. M is like integer, okay, has the following solution. M solutions that are linearly independent So let's see. We have several cases here. If all the R are real, okay, all the R are real, so the solutions are what? E to the Rx, okay, and x e to the Rx. In general, x to the m minus 1 e to the Rx. So what's the meaning of this one? So if our PR is like, if we factored, we get something like this one. Okay. So M is 3, right? And solution should be 1. Okay, for the R solution is 1. Okay, let's use 2 here. 2 is easier to see. So the solution will be e to the 2x is one solution. But this one, because it has multiplicity 3, we have 3 solutions here. The next one is x times e to the 2x and x squared e to the 2x. So we have 3 solutions, independent solutions corresponding to this polynomial. Now let's take a look at the example. Okay, from the example we can see this easily. Now let's see example 1. Determine the general solution to this differential equation. Solution to this. Okay, So we start from the easy one. In the future, we may have more complicated differential equation. Let's see. First step, we write down PR. So what is PR? So we can write down, if you want, we can write down PD firstly. Okay. So PD means what? If we look at here, means second derivative, first derivative, and here's just 2, right? So it's like PD is d squared minus d minus 2. Okay, this is the polynomial. And if we change d into r, becomes r squared minus r minus 2. And corresponding auxiliary equation is this equals 0. In the future, you can skip this step. Okay, you can see from here easily. If I give you third derivative plus 2y second derivative minus like 5y prime plus 6 equals 0, this kind of differential equation. So what's the PR? We can just write down this directly. R cubed minus 2r squared minus 5r plus 6. I should have y here. Okay, 6. So something like that. And the next, we want to solve for r. We can factor this out, like a factor r minus 2, r plus 1 equals 0. And in this case, we know we have 2 r's solution, so which is 2. The other one is -1. And here, multiplicity like a power, they both are 1. So we don't have like that cases like an x in front. So what the solutions are? So solutions are, we have 2 independent solution, which is e to the r1x and e to the negative x. What's the general solution? General solution is the linear combination of those two, so it should be c1 e to the 2x plus c2 e to the negative x. So this is the general solution. We can take a look at this exercise problem, very similar. Find the general solution to the equation looks like this. Okay, y second derivative plus 2y prime minus 3y equals 0. So you can try this by yourself. And here's the solution. Firstly, I write down PR, r squared plus 2r minus 3, and I want to factor this out. Okay, we can factor this out and then solve for 0, which is r plus 3, r minus 1 equals 0, right? So r1 equals -3, r2 equals 1. So what's the general solution? I'm going to write down general solution directly. c1 e to -3x, c2 e to the x. That's all. Okay, so this is when the case when we have the real solution R. Now let's take a look at the second case in the theorem. The second case in theorem means if R is complex number. Complex number, that means what? Means a plus bi, this form, right? When we have complex number, I can give you like a example, like a PR equals r squared plus 1. Actually, you know, if we like a real, for the real solution for this equation, this doesn't have the real solution. Because when we solve, it's like r squared equals -1, no real solution, but this one has complex solution. Okay, complex solution. So for this one, if we factor that one, it's going to be r plus I, r minus I. So solution should be I and -I. Usually for the complex solution, a plus bi and a minus bi, they always like appear as a pair, conjugate. They called conjugate to each other, right? So they always, so if this is solution, a minus bi has to be a solution. Plus minus. So it's going to be a plus minus bi actually going to be the solution. In that case, what is our solution? Our solution is going to be I'm going to give you a little bit of proof here. Okay, so it's going to be e to the a plus bix, like a e to the rx, right? E to the rx, and e to the a minus bix. Okay, they are all solutions. But we are, for our solution, we don't write down this way. We are going to use Euler identity. Euler identity means what? E to the, okay, so I'm going to write down this formula here. E to the a plus bix equals to, we simplify this a little bit, which is e to the ax plus I bx. So this is the real part, that's the complex part, right? And Euler's identity, when we do that one, is going to be e to the ax times cosine bx plus I sine bx. Euler identity, the formula is here, a plus bi. Okay, equals e to the a cosine b plus I sine b. You may have already seen this in some other class, right? This is called Euler's identity. So it's going to be e to the real part, and the plus for the imaginary part, we change into sine cosine. So this is our solution. So we get to continue to look at our solution here. After we change into Euler identity, we get this, and we can write this as e to the ax cosine bx plus I, we distribute e to the ax, e to the ax sine bx, right? So this is a solution. And the same thing, if we do a minus bix, we are going to have e to the ax cosine bx minus I e to the ax sine bx. They both are solutions, and we don't want to write down them as solution, general solution. So it's like for R2, we may have some like a spanning set, so can span the whole R2. For example, 1, 1 and maybe 1, 2 can span, but we like to choose the easy one, 0, 1 and 1, 0. We like to choose easy one. So same thing here. We don't want to choose those two as solution. We want to use easy way to express the general solution. So we can say this is W1. So we can say this is a W1 and this is W2. And if W1, W2 both are solution, so 1/2 W1 plus W2 should be also solution. Let's see. And when we add them, divide by 2, it's going to be cancel the imaginary part. It's going to be just e to the ax cosine bx. Okay, and if we do this way, W1 minus W2 divide by 1/2 here and divide by I. So it's going to be like we cancel the real part of in W1, W2 and divide by I. So we are going to get e to the ax sine bx. We want to use them as the general solution. You can see they're pretty easy, right? Compared to W1, W2. W1, W2 both have two solutions, but here we only have the easy ones. So for the theorem, the second part, when R is complex, if we have this one, d minus R to the m equals 0. Okay, and when we have this case, if R is complex, the conjugate is also solution. Okay, is also solution. as I said before, for the imaginary number, they always appear as a pair. For this case, that means our solution, so that means what? D minus R to the M, D minus R bar to the M equals 0. In this case, we have two M solutions. And those solutions are what? The easiest one, so should be e to the x cosine bx and e to the x sine bx. The first pair, and the second pair are going to be x e to the ax cosine bx and x e to the ax sine bx. And continue. So if we have m here, so going to be m x to the m minus 1 e to the ax cosine bx and x to the m minus 1 e to the ax sine bx. Okay, so this is for the complex part. Let's take a look at the example. Don't worry too much. It looks like a complicated here, but from the example, it's very easy to see. So example 2. Determine the general solution. So just find the general solution to this differential equation. Second derivative plus 6y prime like plus 25y equals 0. Firstly, let's write down PR, auxiliary polynomial. So which is, for this case, should be r squared plus 6r plus 25, right? So we want to solve for r. If we can factor this out, definitely we can easily solve for r. But since for this problem, we cannot factor this out, but we still want to solve for r. So we use the quadratic formula. R equals what? 2a. So the negative b plus minus b squared minus 4ac. This quadratic formula. So 2a should be 2 here. Negative b, negative 6 plus minus b squared minus 4ac. 4ac should be 4 times 25, which is 100, right? So let's see. We are going to have negative 6 plus minus root 64 over 2. And you can see square root 64. Oh, sorry, here should be negative. Negative 64. We're going to get a complex number here, which is 8i. Positive 8i, right? Just 8i. So it's going to be negative 6 plus minus 8i over 2. Simplify, divide by 2. So we get 2r. So the first, so here, let's see, plus minus 4i. So we get two complex numbers. They are r1 equals negative 3 plus 4i. r2 equals negative 3 minus 4i. Right, 2 r's. But for our solution, what do we care? We just care about a and b. So here, this is a and this is b. Okay, a and b. And let's see. So our general solution should be what? y1 should be e to the negative 3 x cosine bx, which is e to the ax cosine bx, and e to the negative 3x and sine bx. Those are the two solutions. And what's the general solution then? The general solution is y equals c1 e to the negative 3x cosine 4x plus c2, just a linear combination, sine 4x, just like this. Okay, we can take a look at the exercise problem. This one, here's the solution. PR should be r squared plus 8r plus 20, and just solve this for r. And when we solve for r, okay, so we are going to get a complex number here. this is negative 16 over 2, right? Negative 8 plus minus 4i over 2. Simplify, negative 4 plus minus 2i. So our solution, so actually what is a and b? Solutions should be e to the negative 4x real part, cosine bx plus c2 e to the negative 4x times sine 2x. So those are the two solutions. They can express all the solutions. Okay, all the solutions. And the general solution is just a linear combination of those two. Okay, this is the example 2. Next, let's take a look at initial value problem. That means we have initial conditions. We are going to use the initial condition to find C1, C2. Now let's take a look at this problem. Determine the general solution to this initial value problem. So here, because the second order differential equation, we have two initial conditions. Okay, now let's see. First step, we want to find the general solution firstly. Okay, same as example 1 or 2. So let's see. For this one, we set up a PR. PR should be, for this problem, differential equation, r squared plus 4r plus 4. Right? We want to solve this for 0. When we solve for r, we noticed we can factor this out actually, which is r plus 2 squared equals 0. Is that correct? Okay, so let's see. It's interesting. This one has the real solution r, which is negative 2. So r equals negative 2, but implicitly is 2, right? So what's the general solution? E to the negative 2x, and do you still remember in the theorem 1? X e to the negative 2x are the solutions. Okay, because this repeated twice. These are repeated twice. So in this case, what is our general solution? We write down general C1 e to the negative 2x plus C2 x e to the negative 2x. So this is our general solution. And we can also write down this in another way, C1 plus C2x. If you don't want to simplify, it's okay, but because we need to solve for C1, C2, so it's easier to write down this way. And next, we can plug in the initial condition. Let's see, y0 equals 1. So y0, when we plug in x at 0, so e to the 0, which is 1, so just C1, right? When we plug in 0 as x into y, so C1, and which is given by 1. So let's write down the solution. I'm going to write down solution. Y equals e to the negative 2x, and I change C1 into 1, C2x. Next, I'm going to use this to solve for C2. I'm going to use y prime 0 equals 4 to solve for C2. Okay, you can do this from either this one or this one. Take the derivative either way. Okay, doesn't matter too much. So we just want to find the derivative. If we do from here product rule, so y prime. So firstly, definitely we need to find the y prime because we're going to use the initial condition y prime, right? Y prime equals what? Okay, I'm going to use this one. C1, which is 1, so it's going to be negative 2 e to the negative 2x here. Let's see, maybe the second, maybe this is easier to find. From here, it's easy to find the y prime. Product rule, but we need the product rule. Negative 2 e to the negative 2x, 1 plus c2x, f prime g plus f g prime, which is c2. Okay, so this is c2. And the y prime 0, plug in at 0, so it can be negative 2 times 1, right? Because this is 0, and plus C2. Okay, when we plug in 0, and which is given by 4, so we get C2 equals 6. And we have C1, C2. So what is our general solution? What is the special particular solution actually satisfy this initial condition? Y should be e to the negative 2x. I just plug into here. 1 plus 6x. So this is the final solution. Okay, and here we can try one exercise problem. We're going to do two problems here. So the first one, solve the general solution to this one. Solve the general solution. So let's see. Solution should be x e to the negative 2x and e to the negative 2x. So the general solution C1 this plus C2 this one. Okay. And the second problem, let's solve this. Initial conditions are okay. I'm going to give the solution, but you can try by yourself. Let's see. Solution should be first step PR. Okay, so this should be r minus 4 squared when we factor, right? So r should be 4m equals 2. So the solution should be e to the 4x, x e to the 4x. Okay, those are solutions. So the general solution should be hello. I don't know for some reason the device was disconnected, but we're almost there. So after we find the general solution, we write down y as C1, y1 plus C2, y2, and then plug into the initial condition and find the C1, C2. That's all. Okay. And the final solution is here, y equals e to the 4x times 2 minus x. We can stop here for the first part of 8.2. In the second part, we are going to do more general differential equations for like R will be complex numbers and with multiplicity different than 1. Okay, we can stop here.